Okay. Good evening, everyone. So today we'll be done with TD learning algorithm. So what we'll be doing is temporal difference learning, linear function approximation. We'll be learning how this algorithm actually converges. So this one of your assignment questions could be to implement this algorithm, but for now we'll be seeing if the algorithm really converges. This is one of the theoretical classes that we'll be having. Mostly we are not going into proofs and things like that. But I think today's one will be a bit interesting. We'll be doing some uh, fun questions of probability, and that I think will help you a lot. So let's get started. So if you recall, what was the big picture of the what we wanted to learn? We said that the value function v pi of a state s was parameterized by a vector w, right? So I had features and I had weights. So everything would be algebra and probability today, but to remember this is important. What is the big picture? So what was the big picture that we went out trying to achieve? We said that the state space is too large, then we or uncountable, then we could approximate the states using a feature vector, right? So for every state is equal to 1 and all the way, we could have features f1, f2, dot, 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 fn, such that we learn the value function w, or weight vector w, such that w1 phi s1 plus w2 phi s2, so dot, 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 all the way to wd phi of sd. These are all the columns 1, 2, 3, and this is d features. This represented the value function of the feature of the space of the set of the state S. Right? State belong to the state space. This is what we said. Any questions? Anything you want me to revise regarding this? So we said that since the value function was uncountable, we could not really represent it in a matrix. So we would have to parameterize it by having so where similar states would be grouped together. That's the idea. And given a novel state, that is a new state which the value function has not seen, we can still fit it into the feature vectors and still get a value function for the state. This was a advantage over tabular methods, right? Tabular methods, no generalizability, right? No, cannot deal with new states. New states. And we had seen the function approximation idea can deal with new states. So, okay, we saw examples regarding we're seeing cars and uh, cycles and how the states could be defined. And okay, so this was what we were trying to do. We had set out to learn. But now, how did we try to learn this? Do you remember? How did we try to learn the features W? So we said that the squared error must be minimized. Yes or no? Where S is sampled from d pi and W is the vector, right? Isn't it? This is what we tried to do. We said that the MSE loss we should minimize over W. Find the weight vector W such that the above loss is minimized. Right? And we said that this is the. So how did we represent it as a vector? We represent it as a vector as v pi minus phi of p of W transpose d v pi minus phi W. Isn't it? So we said that for every state, so this is a RS, and this vector is S cross D, and this is D cross 1, isn't it? So we took the linear combination of the features. So phi 1, phi 2, dot, 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 phi D. And we take the linear combination with W1, W2, WD. And we say that that is equal to V pi. That's what we are trying to do. We are trying to learn the best function that does that. And we said that if this D matrix was not there, what would this be? This would just be the square of the individual components. Yes or no? If we write delta as V pi minus phi of S or phi of W, what would delta transpose delta be? Anyone? Am I audible? Be summation of I equal to 1 to n, 1 to here D in this case, feature, each of the feature vectors. It's the dot product, right?
Yes.
So now what I'm trying to say is, so if I have a D matrix over here, all it does is D is a diagonal matrix, as you know, is a diagonal matrix of D1, D2, dot, 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 D, DD is you just multiply the diagonal element with this, isn't it? So this is basically you're taking a weighted distance. So it's basically, let's see what does this mean. So this means it is the, so if delta, and if I put a D over here, I'll just put it in a different color. Then I will write it DI, right? So this is what I want to mean, that the elements DI would just weigh the individual components. DI is the weight to each delta I. Okay, that is also fine. So now what do we want to understand? So for the first thing, say you want to learn a matrix or a vector or this vector X. So all I'm trying to say is, what does this represent? V pi. What does minimizing this represent? V pi minus phi W transpose V pi minus phi W. What does this represent? Geometric view of this. Minimize over W. So V pi is known. So do you agree? What is the space over which we are trying to optimize? Can you tell me? What are the elements we are trying to optimize? What is the value we want? We want a W star, right? That minimizes this. We want this is the space over all W's. Do you agree? So this plane, if I consider, what is this plane? Can you tell me what would be this set of this plane? So that, see, so V pi, and after I learn this W star, the predicted V pi would be just phi of S transpose W star. Yes or no? Do you agree?
Yes.
This is the predicted value that you will have. This is the predicted. Once you learn the W star, this is the actual value. So you can clearly, as Antariksh was telling me last day, so this, if W was a vector in Rd, so this would be it's just the linear combination of all the columns, isn't it? So this is just the space of column space of features. Fine. That is, we are considering all linear combinations of feature space of the features in phi, right? So this is all we are trying to do. We are considering all the features, linear combination of all the features in the, so if this is phi 1, phi 2, phi 3, and so on. So we can take the linear combination of W3, W2, W1, and you may get a W. Say this is W star, which is a linear combination of these sets. So see, whenever you're minimizing the distance between a V pi may not exist in this space. V pi may be out of this space. If you are wondering how, this is because you have to read a little bit on the linear algebra. But the idea is all the vectors in the column space, this need not be R fully. So what I mean to say is V pi belongs in RS, right? So this is a S dimensional vector, but this vector space that I have over here could be only a subset of D dimensions because we have only D or S feature vectors or whatever you are considering. We are taking a linear combination of, so this is a subset of RD is what I'm trying to say. So we cannot directly get a vector that would be equal. This equality will not hold. What we'll get is we will get this. This is called the mean or the squared error. So we will minimize this error. So V pi is this vector. This is the linear combination. This is pi W star. So this is what is the error vector? Error vector is, can you tell me?
V pi S minus site transpose V star.
Correct. So this is the vector form. So you can see there you have a vector here and you have vector here by the triangle. By the triangle rule, I can write down the error vector is this. So all we want to do is minimize the error vector. That is, we want to learn a vector W star such that it is just the projection onto the plane. That's all we want to do. See, all these things are done last time. This interpretation. You can go back and look. I'll put the description. I'll put the link in the description where we have done all these projections and column space and so on. If you are not familiar, please look it up if you are interested. This is just a nice way to visualize what things are happening. So basically, the value function may exist in a S-dimensional space, but we want to project it into a D-dimensional space of the feature vectors. So that's what we are all doing. OK. So now, but we are not doing exactly this, right? What are we actually doing? We are doing D times V pi minus phi W transpose V pi minus phi W. So we have this weighing vector D that is matrix, weighing matrix D that comes in. So let us represent this as delta and this as delta tilde. So what I want to say is, or let us say this is V. I have used V. OK, so V transpose dV. OK, what does this actually mean? Say I put a square root again on it, and let's try to find that out. So first of all, tell me what does this mean? Of a vector, the L2 norm of a vector mean?
It's not this length of the vector.
It's the length of the vector. The length of the vector. Length of the vector. And that is basically the inner product of the vector with itself, correct?
Yeah.
Yes.
This is the Euclidean distance from the origin. Euclidean distance from origin. So clearly we know that. So any vector this is x1 squared, and by Pythagoras theorem, this is x2 squared. So this vector becomes square root of x1 squared and x2 squared. We keep on adding components. You can always add plus squares, but this thing remains the same. So this is basically again a dot product of the individual components along x and y and z. And if you have multiple directions, you keep on doing that. OK. So V transpose V is fine. So now, what is the induced vector norm? So this is, we have seen is the square root of V transpose dV. Yes, everything is same. Here we had an identity vectrix. Here we have a induced by a D vector, which is again a diagonal matrix D1, D2, dot, 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 dt. Correct? Fine. So now, can I do something about it? If di greater than 0, which is our case because these are probabilities, then can we write this as square root d into square root d, where square root d
Yes.
is?
I felt that I would tell it to you, but yeah, it's only for positive.
Yeah, but these are probability matrices, right? So this is a probability matrix.
Yeah, like this is how we like broke it for positive definite matrices as well.
Correct, correct. Exactly. So this is what you will write.
Yeah,
this
I was
as
thinking that this is a positive definite norm. I think there was something like
exactly,
that.
exactly.
Yeah.
This is so because these are all positive. So this is, you can write this as dv transpose dv. The diagonal matrix transpose is always a diagonal matrix, the same. It's a symmetric matrix. That's why I can write that. So this is nothing but the L2 norm of this. Correct? So this is basically nothing but the length. It is the length, but the components are readjusted. The components along each axis is readjusted. So if you are wondering why I am saying that, see, clearly just multiply this with v1, v2, dot, 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 vd. What will you get? You'll get this matrix. d1 times v1, d2 times v2, dot, 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 dv, dd times dv. See, all the components are just readjusted. That's all what is happening. So that's all for the geometric interpretation. So what happens is you end up learning. So if this was your this was minimized by v pi minus phi w squared, you now readjust each of the components. So you'll end up learning this vector, which is minimize w v pi minus phi w d square. So this need not be orthogonal to the plane, but what we end up understanding is, so this would be just a projection, just a combination of the rotation of this vector by scaling each of the components up and down. That's it. Okay, so now this was just a revision that we were doing. So let us try to write down the stochastic gradient descent algorithm for the TD0 algorithm. Okay, so first of all, what is the gradient descent algorithm? We said Wt plus 1 until convergence is the loss, or here it is eta w dw, correct? This is what we were saying. The intuition being, if a ball is here, just roll around the gradients until you reach the minimum, correct? So now your loss function is half of, we're just putting the half for the ease of our computations. P transpose S W squared. Okay. S in S. Yeah. Now tell me, what is this going to be? We have derived it last time. Do you remember? This is minus summation of S belongs to S, d mu of S. Again, I'm writing mu somewhere, pi somewhere, just this will be pi only. Wherever if there is a mu somewhere, please ignore it. Okay, now tell me the derivative of this. We derived it last time.
Yeah, only that term will remain and all the other terms will be.
We had a phi of S, yes or no? Correct? Because we are taking a derivative with respect to W, this phi S will remain, as you are saying. Okay, so to check if it is correct or not, what is the dimension of this feature vector? This is phi of S is a feature vector, right?
Yes, it's a
Yeah,
dimension
S.
plus d.
It's one vector just for one state. So it will be,
Yeah, it's one dimension.
D-dimensional.
Yeah, 1 cross D.
Yeah, correct. 1 cross D or D cross 1. We don't write. So D cross 1 is what you write, or just write D. Correct. So now you see the W, the gradient of W again is D cross 1. Yes or no? Because it's the sum of, these are scalars. This is a real number. This
Yeah,
is a real number. This is again R
Right.
cross
So,
D. Yeah.
is it fair to say that there are S feature vectors and each of them are right? That's the thing.
Correct. Each
feature
of the
vectors,
yes.
are D. Yeah.
Yeah. So you see, whenever you take a gradient, I don't know if you did it in your engineering physics already. So if you have a scalar y, you have done it in class 11 and 12. If you have a potential, for example, V, and you take a gradient of the potential, you get the force, right? Or the field,
Yes.
whatever. What does this actually mean? It means that you take the gradient of take partial derivative with respect to x, I roof, plus partial derivative with respect to y. This is what you used to do in your school days. Z, K roof. This is all you used to do. Here also we're doing the same. We're just stacking it in a vector form. So gradient with respect to the scalar is the derivative of each of the components as we derived it last time. Okay, that is fine. So what is this? How can we write this as? We can write it as the expected value of, see, this is a probability function, right? So states are sampled from the d pi distribution, the stationary distribution, right? D pi of S is the stationary distribution of the MDP, yes or no? We have discussed this last time. Stationary distribution of the controlled Markov chain. Correct? So we are sampling the states based on it's an expected value, right? It's just lotus. The probability of being in a state into the value function. So it's just this V pi minus phi transpose S W P of S. Do you agree?
Yes.
Okay, so now we showed that last time that if it is really an expectation, we did not need to compute the entire sum, right? The stochastic gradient descent gave us this option. What did it give us the option of? Of using an unbiased estimator. Right? Of using an unbiased estimator. This gave us an option of using an unbiased estimator. So what does an unbiased estimator mean? So you sample S from d mu of the distribution d pi, again, d pi, the stationary distribution. After sampling the stationary distribution, what do? You say, I am not normally, how would you update? You would update it like, because this is the gradient, you would update it with the expected value of, this is the just gradient descent. States from V pi minus phi transpose SW pi of S, right? But SGD tells me since it is an expectation, it is an unbiased estimator. So I can just sample S based on this. Just sample S based on d pi and do this. WT minus WT plus eta V pi S minus, right? This was your SGD that we derived last time.
Yeah. So only one state, right? In SGD.
Correct. Only one state, and you can update at every time. So you go to the next state and update for that state. Instead of taking an average of all the states and updating once, you update S. By the time you complete all the S states, you have updated S times, right?
Yeah.
This is one update for S states. This is S updates for S states. Great. So now, but there is a big problem. So I have noted this down over here, but So I have, did I write it down? Yeah, I have discussed this. I have discussed SGD, implementation and so on. Okay, fine. So now there's a big problem here. So for this equation that I have over here, how do I know this? This is a question mark, a big question mark. So we could do a Monte Carlo and as we have done before and get the V pi's, but V pi of S is what we are trying to learn, isn't it? This is what we want to learn, correct? Yes or no?
Yes.
So this doesn't make any sense. This is already unknown totally. We can do some computation, some algorithm and do the Monte Carlo estimate and put the value. That is fine. But that is going to be very slow and that is not very principled because this V pi of S is what we want to learn and that is in the equation. That is a ridiculous thing to actually see. We shouldn't have it in the equation at all, V pi of S, because this equation should only depend on constants and W, right? Fine. So again, this will be WT because we are updating at the Tth instant. That is fine. Great. So now, how do I deal with this? So let us recall what is V pi of S? Do you recall? So let us write a discounted setting. Discounted setting. So from t equal to I0 to infinity or I equal to 0 to infinity. So it's an infinite horizon problem, whatever problem you want to solve. So this will encompass everything. So what will we have? Gamma to the power I, the reward function between state st, at, and st plus 1, I plus 1, sorry. Correct? Yes or no? Given st is equal to s. Do you agree? This is the reward function. This is what we want to learn.
Yes.
Yes.
So the ATs are sampled from what? Do you remember? The actions are sampled from the policy, right? Do you agree? So for a particular state, you say that which action is the best. That's what RL is all about, right? And st plus 1 is sampled from st and at. This is the controlled Markov chain. Okay, so again, let us revise how to do this. So can anyone tell me the steps how to do this? How to get an equation for this? One step Bellman equation.
Yes. So first of all, we divide the I equal to 0 and I equal to 1 to infinity terms.
Okay, I equal to 1 to infinity. I put it from 0 to infinity again, and I put a gamma outside.
Yeah. Yeah.
And I put a gamma to the power I, and I put st plus 1, you said, right? Starting from 1.
Yes.
At plus I plus 1, st plus I plus 2. Fine, I do that and I separate the tth term out, right? Do you agree?
Yeah. And then I'll take a iterated expectation and the summation gamma to the power rst plus 1 plus I. If I would include that into another expectation.
Very good. So this is what I want you to take away from this course. Whenever you have anything that is unknown, you keep taking expectation until the time. If you have an expectation outwards, you can keep on taking iterated expectation any number of times. We have proved it also before in the class. This is S dash. Okay, fine. So now, so this becomes expected value of RS A S dash plus gamma times V pi of S dash. St is equal to S, right? We get a recursion. That's all we got, right? A recursion. That is V pi of S. Do you agree? You remember this equation?
Yes.
So here again, these are the two sampling variables over which expectations have been taken. But now, why did I do this? Just look at the Gradient descent update. What is the gradient descent update here? What is the gradient of this? Just remind me. This is the expected value over d pi, state sampled from d pi, v pi of s minus
phi transpose
SW
into the weight.
into the phi of SW, right? This is what I got. Negative of this, right? Fine. The gradient of the loss. Gradient of v pi minus phi w squared. Fine with everybody? Very good. So now, what will I do? Can you tell me? I'll do one step which will simplify the things further. See, I have found out v pi of s, right? Do you agree? Okay. I found out v pi of s in terms. Good. So let us try to write it down. So what will it be? S in terms of d pi. And this expectation is another expectation, yes or no? I'm just writing v pi down. So r s a s dash plus gamma times v pi of s dash. St is equal to s. Do you agree? Fine. And I have a few constants over here. The constants can be taken inside expectations. Do you agree or not? Let me write one step, then it will be clear. So I just wrote v pi, pi transpose. I will not skip this step. You may just not understand then. So let us try to understand what did I do. This is your v pi. Do you agree? V pi of s. Fine. I just replace the v pi of s over here. This is exactly kept. This is exactly kept the same. Fine with everybody? Okay. So these are constants. If s is known, right, which is already known, we can see in this internal equation, we already know st. So we can just take this inside this expectation and write everything together. d pi expected value, two expected values, reward of s a s dash plus gamma times v pi of s dash minus phi of s w into phi of s. Okay, fine. St equal to s. Do you agree? Fine. All I wrote is I wrote down the entire equation together. I'll take a moment. Just please ask if you have any doubts. I'm putting all brackets to help you out. Please ask. So what is the inner expectation over? Can you tell me? Firstly, in the inner expectation, what is known? Tell me that if you have understood. In the inner expectation, what is known?
Action is known.
Just check the inner expectation. See, this expectation is a function. This value is given up to this much. This is the value. This is the function, and it is conditioned. Something is conditioned. You already see something is conditioned for that expectation. So consider this is a function of s, a, s dash, and w. Right? Let me write it down. Let me write this as f of s, a, s dash, and w. So this is nothing but what? S in d pi, expected value of s, a, s dash, w, given st equal to s. So what is known and what are not known is what my question is. So w is a constant. We're not going to deal with w further just yet. What else is not? What is not known? What is known first? Tell me.
S is known, but we don't know S dash.
Correct. S is known. This is known. because I am fixing S. I am already given the value of S is given. This is given to me. Whenever I condition in an expectation, please go back and look at the conditional expectation. It will be very useful. So whenever I am conditioning something, the internal function just becomes a function of that random variable is what we tell. So basically, this function is known, and we will take expectations over S and SW. These are stochastic terms. So now tell me, how is A sampled from?
It's sampled from the policy.
Correct. And your S star is sampled from the Markov chain. Good. So now you see this entire equation can be written as a single expectation, isn't it?
So could you just explain the calculations, the manipulation from second to third
all
step?
I did, I'm doing. So V pi of S that I wrote here. Okay. I wrote this. This is clear. Okay. So now I know the derivative of the gradients. The gradient, I mean, I know the gradient of the TD0 update. That is also fine.
Yes, I mean, from second state to third state, what you have done, please explain once.
Okay, so now I just put the V pi of S currently over here. I have done that is also clear. You told me I put the value of V pi from the Bellman equation from 1. So I put the value here, and now what I am doing. So you have an expectation, yes or no? This is an expectation, right?
Yes.
So what am I doing? So expected value of X minus A. Can we not write this as expected value of X minus A by linearity of expectation?
Yes, we can.
This is the constant. So when it is a constant, I can just take this inside the expectation. Do you agree? By linearity. Linearity. That's what I have done. That is fine.
Yeah.
So when I put that in the inner expectation, I also have this term, which is also a constant. Similarly, we know A times expected value of X is same as.
Yeah, it is okay.
Yeah. Good. These two things I used to write it into a single expectation. And so you get expected value of X. We will not write the expectations. So we will write it over here S as d pi of S from this, then action from this, and S dash from this. That's all we're going to do. Very good. So now we can write this as a single expectation of S, A, S dash. Or you can even write it as ST, AT, ST plus 1 plus gamma times V pi of ST plus 1 minus V pi of ST W times V of ST. This is the expectation I'm dealing with. Okay. So this is a scalar. This is not a C. This expected value over S is only in the inner expectation, not in the outer expectation. Remember that. So if I have made a error in putting brackets, please forgive me. I think I may have. This is expected value should be here. This is fine. Yeah, this is fine. So this is clearly a scalar value as the loss we expect to be. But now, as soon as you see this, what can I write the gradient to be? So this is the gradient. So now if I have to do gradient update, what can I write? Can you tell me? So SGD update, as soon as you have an expectation, you can write this as okay. We have discussed this. We have a negative sign over here. Please note. I forgot to put the negative sign. Yeah. Tell me.
We would just take the function.
Just take the function, right?
Yes.
You just take the function.
This function and not the expected.
So we don't need to compute the expectation. We can just by SGD's convergence, we can show or use this ST plus 1. See, now this equation looks better. I have this reward term coming in and I have the value functions coming in. But still there is a big catch. Right? Can you tell me? What is the catch? There's a catch over here.
We don't know the value function or st plus 1, do we?
Yeah.
Because that's again
No. Correct, not known. But at the end of the day, what do we want st plus 1 value function to be? At convergence, what do we want it to be?
equal to
P transpose st plus 1 W star, right?
yes.
So Sutton got this idea that at convergence, if it is true, why not just replace this with WT and see if it converges? We'll see if it will converge. So as luck would have it, replacing this at the iterative step as this update allowed it to work. So this is the implementation. The reward at ST, AT, ST plus 1 plus gamma times phi transpose ST plus 1 to W minus phi transpose STW into phi transpose ST. So this becomes your update equation. So this is what I'll be dealing with for the rest of the class. So we have, so for one step Bellman equation, we have found out that first we derived the update step and then we said this is not possible to implement. No. To overcome this, Sutton said we're going to update the next states st plus 1, the value function, using the same approximation. Use the same approximation. So that solves most of the, so the algorithm becomes very simple. So the algorithm is, so until convergence.
It's I have a silly question,
What?
but
Yeah.
like, can't we replace? Oh, sorry, we can't replace. I was having the idea if we
Exactly.
could.
I was going to ask this entire same question to you, but you asked it. That's great. You're following. So why not replace the
Yeah, I saw the equation and it's
this? You cannot, because if you replace this, it becomes 0, right? This replacing does not work. Doesn't work as gradient becomes 0, isn't it? There's no learning that will happen. This you cannot replace is not equal to phi transpose STW. This is the exact question I was going to ask. I'm so happy that you asked. Fine. So your update is, say, sample a state ST from d pi distribution, then sample an action based on policy, then until convergence. This will be outside ST from d pi until convergence ST plus 1 comma A. Then what do I do? Just update. So you can set WT to be zeros and WT plus 1 as WT plus eta times. So we have to write this equation multiple times today. So let us just write it down. So observe the reward. Observe reward ST, AT, ST plus 1. So this is ST, AT, ST plus 1 plus gamma times phi of st plus 1 w t p transpose st w t I of st. So please, so this will be ending over here until you are converging. That is the algorithm. It's very simple. Everything is known now. So this can be implemented. So now, if so, the engineers would do this, that what they would do is say this is an algorithm and try to evaluate empirically. But especially in mathematics and in science, we have to, at least theoretical stuff, we have to say that we derive an algorithm. We can't just show convergence empirically. We need to show, does the algorithm actually converge theoretically? And if it is converging, where does it converge? So the agenda of the next part of today's presentation is, does the algorithm converge? And if it converges, where does it converge? Okay. Fine. So to understand that, let us take a simple. So if it converges, where does it converge? Is the first question I'll ask. That is the second question in the list, but I'll just show you. It's easy to compute like this. Let's try to see where does it converge. So how do I say where does it converge? Can anyone tell me? So do you agree WT should be equal to W star as t tends to infinity? This is the property of any iterative algorithm. Okay. Right. Your weights must converge at t equal to infinity. So what I say is, say if I do WT plus 1 minus WT. This is a hand wavy explanation, but this will help you understand the proof that I will do next. So I'll just write it in a different color for better understanding. So WT plus 1 minus WT is equal to eta times expected value of R. So I'll just write this as R ST, okay, ST, AT, ST plus 1 pi of ST plus the expected value of, okay, I'm taking an expectation on both sides here. Okay, with respect to W's. So second expectation would be plus pi of ST. What will I get? Can you tell me the second expectation? What will I get? Okay, I'll remove the, yeah. For the timing, I'll remove the expectation for your understanding. Just do the algebra. So I take WT this side. And then what else?
Gamma phi t of st plus 1 into
Okay.
W minus phi transpose st of the st into W.
Good. See, so what I'll do is this ST is there. I will just multiply it. Since this is a scalar, right? Everybody agrees. So dot product is a scalar.
Yes.
So this is a scalar. Again, this is a scalar. So phi transpose W is a scalar. That is a real number R. So I can put phi S somewhere here, and that's not going to change anything. So what I'll do is I will write this. I'll write it another step for once, and then you can follow. So I'll write this as gamma times phi of st plus 1 transpose W minus phi of st transpose W. Okay, so I'll get this is equal to WT plus 1 minus WT is eta times rewards ST plus 1 pi of ST plus, what can I take common over here? I can take ST common. phi of st common. And I can write this as P of gamma times phi of st plus 1 minus phi of st transpose W. Yes or no? I can write this. I just took st. I just pulled out st as common. Fine. Okay. So now if I take expectation on both sides, these will become scalars. Right? So this would be, can you tell me what would be? This is a vector or a scalar? Or a matrix? What is this going to be? Any idea? This is
Ask you
phi of,
something before that.
phi of,
How did
yeah.
the other gamma come from? Like there was only one gamma, right? Like
I think that there is only one gamma. I wrote, I made a mistake. I didn't write two gammas. Oh, sorry. I have written one more gamma. Sorry. Yeah. Thank you. Yeah. So I'm telling what is the first expectation over here? Thank you. Is it a vector or a matrix? What is it?
Yeah, is it a vector?
It's a vector, right? Because see, this term is a vector. This is an RD, and this is a
Yeah,
scalar. In
and
RD.
that's scalar. Yeah.
So we'll write this is equal to B. Say this, write this as B. So this becomes eta times B. And this we will write as, say, minus A. What is minus A? Let us try to understand. See, this term, phi of S T, and this term, phi of ST dash. If we just compute the dimension of this, we will understand. So do you agree? This is S cross 1. S cross 1, and this is 1 cross S. Do you agree? Or 1 cross D? Fine. The D-dimensional features.
Yeah.
So this is an outer product. So this becomes D cross D. Do you agree? Matrix. It will become a matrix.
yes.
Yes.
So this would become a D cross D matrix. Again, I will just check once. D cross D matrix. Okay. Very nice. P of S. Am I making a mistake? W is RD. Oh, it's fine. B is also D. D cross 1. Sorry. I thought B was S comma 1. Fine. So D is, this is D cross 1. So now, on expectation, if it has to converge, what does this term has to be at t equal to infinity? T tends to infinity. The expected value of WT plus 1 minus WT, what does it have to be?
0.
Very good. It has to be 0, which means B must be equal to AW star, which means W star is equal to A inverse B. So now we'll see what this A and B's are. We have already found out some terms here. We'll find out the exact terms. So basically, what are we trying to do? This is converging at B minus AW's solution. So it is not exactly a solution. Getting so B minus AW is not the same as V pi minus PS with respect to W with respect to D. So it doesn't really converge at D where we want to converge, but it converges at a different point, which we'll find out exactly. So that's the first takeaway point, that we are actually trying to minimize in this case this equation. This converges at the fixed point of this equation and not the original equation that we had, that is phi V pi minus phi W D naught. Is that clear? So when we have this equation, this is basically, let me just make it clear to you. So say you have A equal to A x, right? Fine. If y equal to ax, then x is equal to, if a is invertible. Do you agree? Yes or no? Else we can compute the Penrose inverse.
Yeah, pseudo inverse. Right?
Yeah, but pseudo inverse is basically nothing but this. This is a pseudo inverse where you minimize x cap. That's exactly a pseudo inverse. So you do this, either of them you do. And basically what I'm trying to say is, so this is effectively both are the same as projecting it onto the column space of A. So you see here it's a altogether different problem. This may turn out to be same, but this is not the same as V pi minus phi W d norm square. We'll see if it is not the same. So it converges not to this point. It does not converge to the minima of this, not to this minima, but it converges to a different minima. That is minima of the above equation. Converges to minima of this. So we'll understand this as we go ahead in the how does the solution happen, or how does the convergence happen. So let's try to understand how does the convergence happen now. So now we have understood that if it converges, it is not converging at the point we want to converge, but let's see if it converges at all. To understand that, today I'll give you a brief flavor of stochastic approximation algorithms or stochastic differential equations. I have given this flavor once when we talked about, remember Bandit's algorithms, right? Where I told you what is a martingale and so on. I'll tell this to you once again, but in a much more intuitive manner. So again, as you can recall, so this is the update that I have. Do you agree? This is the form of the update. Xt plus 1 is equal to xt plus alpha t ht. Fine. This is the update equation that I have. So h of t, h of xt is the derivative of t of x with respect to t, is what I'm trying to say at time t. So, or any loss function we want to minimize over x. It's fine. There's the same thing. So what am I trying? What I'm trying to say is, say if you're taking a derivative, in this case, let's take the simplest example of d, where we just take the derivative with respect to x. Right? Tell me that, do you remember this equation? The equation, let me just write it down here now. A little bit fresh. So an ordinary differential equation in Euler form. First tell me xt plus 1 minus xt by some parameter, say alpha t. What is this? Or delta t? What can you write this as? Can anyone tell me? Xt plus 1. Okay.
As a function of xy, which is basically the first derivative of x.
Very good. So, like, if you are trying to remember your school notation, we can write it this way: y is equal to f of x. Right? So you could write yt plus delta minus yt by delta is equal to f dash x, or the derivative of y dy dx. That's the definition of derivative. Yes or no?
Yes.
Good. So now what I do is I say x is equal to t, y equal to x. That's all I'm doing. So x is equal to, say, So instead of this, I will write this, I will overload this notation and I'll write x is equal to x of t. That's what I'm going to write, basically. So I can write this as the first derivative of x can be written as, so this is the first derivative, dx dt can be written as xt plus delta minus xt by delta. So this is equivalent to writing xt plus delta is equal to xt plus delta times x dot at t. Do you agree? Fine.
Yeah.
Yes.
Approximately equal. This is called the Euler form. So Euler form we discussed that time is that if you have a point here, you go delta along x, you go delta, you multiply delta x, and you multiply the tangent at that point with delta. And this was your xt. This xt plus 1 would be xt plus x dot t of delta. We can clearly see from the graph. Yes or no? So this is theta, tan theta is equal to x dot t. Right? So tan theta is equal to x dot t is equal to perpendicular by base. That is y bar by delta. So y bar is equal to delta x dot t. Therefore, xt plus 1 is equal to xt plus y bar, which is equal to xt plus delta into x dot t. So basically what I'm trying to do is just using this triangle, I am going from this point to this point. That's it. So I represent a x dot of t as say h of xt. This is your Euler equation. And I say, I write it as a difference equation. So I say so this is the difference equation form. In a computer, you cannot really go delta tends to 0. So you have to take one time point, and this is what you'll get. So in this case becomes the learning rate, whatever you want to have. So delta becomes, you're replacing delta with eta. Any questions? So this is your Euler form, or the ordinary differential equation can be written in this form. Any questions? Okay. So now, the ordinary differential equation is something like this, right? So if you take a, so this is t, this is x, this is the position time graph, and the say at this point, this graph asymptotes, right? So do you agree that x star, this is called a fixed point or an asymptote? Okay, this is called a fixed point or an asymptote. What does it mean? Just look at this point over here. Do you see the derivative is 0? Yes or no? Fine. At this point, you can clearly see that horizontal tangent. Yes or no?
Yes.
So
Yes.
now xt plus 1 is equal to xt plus eta into some delta which is tends to 0. So you see that xt plus 1 tends to xt. So this is this is called a fixed point. So now this is for an ordinary differential equation. You can have any differential equation which is having as asymptote, and you can write it down in this form, and you will have a fixed point that this equation converges to. For example, you can have an equation that goes and converges to this, where radius keeps on decreasing and you complete a circle, right? This is also one more possibility, where your theta is maybe 2 pi. So omega is equal to 2 pi by omega t is equal to theta. So you will write omega t as theta, which is continuously changing, which is omega could be the angular velocity, and your radius could be just a function of 1 by r. So that's what this equation may be converging to, just 1 by t, for example. That's it. So as time decreases, your radius keeps on decreasing, and omega itself will be a function of time. It's a function of time. So it's like 2 pi. The 2 pi is the angle, is the at an instant the circle's diameter. The 2 pi r is the diameter of the circle, and so you want to travel, say it in some capital T amount of time. This is the capital T amount of time. So this is your angular velocity basically. So what is this? So this is one of the examples that you can have. So where your radius keeps on is keeping on decreasing, and your omega similarly is fixed. So in this case, it could just be 2 pi by time, something like that. So at any time you can have a constant. So I'm just making a mistake. Just give me a moment. At a particular time, say you have this equation, you have a circle, right? So this circle, the angular velocity is 2 pi by the time you want to convert. You want to rotate along this circle. And so this is the radius is r. So this is your angular velocity, and the radius at r is, say, dependent on time by 1 over time. So it decreases, the radius decreases with time. And at every time, for every radius, you have a constant velocity omega. And that is just, so your theta at a particular time t would just be, can you tell me, omega into t. And omega itself depends on what is the omega instantaneous axis velocity of that point. So that's basically what it is currently. So what are we trying to say is this would have a fixed point, right? So your radius would decrease and you would fall onto this, my minuscule point that you are going to fall on. You're at a particular time, this is r comma theta is what I'm trying to say. This is our radius and the angle at which you are. But what the major point of discussion over here is say that if this was not an ordinary differential equation, but you added a noise term to this, plus a noise. So that makes it a stochastic differential equation. Stochastic differential equation. Right? So your ordinary differential equation h of xt is there, which is the derivative, but you cannot explain all the derivative, and you say you add a noise mt plus 1. This is a noise term. What does a noise term mean? It means that you will converge, but you will have a noise, so you will move around that point of convergence with some noisy effect. So for at a particular time, you can just go up, down, around the. So this was your expected trace. So but at a particular time, due to noise, this can vary. Right? This can just vary about that expected trace. So what we want to learn is this noise, does this noise go to 0? And if the algorithm converges in expectation. This is all we want to know. Okay, so any question?
In bandits, there was RT minus QT, and I think you introduced expectation of RT, right, to manipulate the
Yes,
thing.
we will do the same over here, but did you understand what is the idea, large overall idea? Any questions about that? So currently also we'll do the same. We will change the noise term here and there, and we'll try to see if that is working. But what I'm trying to ask you is, are you able to appreciate what is happening over here? Like more than that is like what I'm trying to say is you are going to converge to an asymptote, but when you converge, you will have a noise term there. So that is going to make things difficult for convergence. Rest of it is fine.
Yeah.
It's like introducing a damping.
Exactly. So you would try to see that if the effect that you're seeing damping could be expressed as a noise term, but is that noise important or not? Does that noise go away to zero or not? That's the question you are going to we're going to ask. Fine. Okay. So you could, for this equation, I was just being a bit tidy. So your angular velocity could always be constant as well. It does not be a function of time. So you could rotate along the circle faster. It doesn't really matter. So theta t. So this velocity could be a constant again. But the main idea is that see RT is decreasing, so it will fall to zero. Correct? That is fine, right? You will go around a circle, but you will fall onto a center. But that is okay. So what we'll try to do is, so like bandits. So we want this noise term to be zero on expectation. That's what you were saying on Antariksh?
Yeah, we did that for bandits as well. Like
Exactly.
in bandits, I remember that you defined a term called martingale as RT minus expectation of RT, and then you took the expectation of the
Exactly.
term and you said that it would be expectation
Go
is
to
zero, and
zero.
so the martingale converges to zero on the long run.
Exactly. So that is exactly what I'll do today. I will do the concrete proof of that. So that was a hand wavy proof. Today I'll be doing the concrete version of that. Okay. I was not sure if I would do it, but I saw that it is fine. It's easy only. There's not a lot of difficulty. So see, what is actually happening at every point, you have a derivative and you have a noise term which fluctuates your transitions. So the idea is, if does this noise sequence go to zero in expectation? Clear to everybody? No questions?
Yes.
That's all we have to say. If it is going to zero, then this term just becomes an ODE. And then I know there is a unique solution to an ODE. If it has an equilibrium point, it'll always have that solution. Okay. So now there is a result from Borkar. This is a famous result. We can't prove this. This is a very, very involved result from stochastic differential equation, but we can use the result. What does the result say? That for a stochastic differential equation of this form, this converges if the following holds. That is, if the function, say I have a, where is my stochastic differential equation? Here you go. The h of, so you have two terms over here. One is the xt term that you are optimizing over. Xt is the optimization term. And you have y, which is a Markov chain. This is exactly the two things I have in an RL problem. This is my W and this is my MDP. Do you agree? These are the two things I want to consider. So of this form, and there is a martingale sequence that I have, MT plus 1. I'll define what is this martingale sequence. Then, if this function is Lipschitz continuous, we'll see each of this term in great details. And if the martingales are square integrable, and if the xt's are bounded, which we will assume, this can also be proved, but we'll not prove it. If the step sizes are like the Robinson-Monroe algorithm, and if yt is a part of a Markov chain, then we have a solution to the of the SDE converging to a ODE solution. So let us try to see each of this case one by one and try to validate it. And then we'll be able to prove it. So what do I say again? I will not read it out again as I never do. So I'll try to just write it down. Xt plus 1 is xt plus some learning rate h of xt comma yt plus martingale of mt plus 1. It says that if the update rule that I have over here has a martingale term like this, and all these conditions satisfied, then I will have a solution. And let us try to see if we are having that type of a solution. So first tell me what is the TD0 algorithm. And I will try to relate the TD0 algorithm with this result and try to prove it. The TD0 algorithm says that Wt plus 1 is Wt plus, tell me, some eta t
Times the first temporal difference, which
reward
is
st plus 1, then
plus the value function of st
plus 1, then
it's minus gamma t of st into wt for like the TD0 algorithm. In the model free one, we were approximating v pi of s, but it's the same thing here.
yes.
The gamma was 1, and here we are just taking a more general.
So now this you see this equation is not a martingale form, right? This does not have sum of martingales and so on. So now I have to do something to make it a martingale, make it all this hold. So I have to convert this equation into this form. So first let me write this equation in a shorter form. So let us represent this equation as some f of st, at, st plus 1 and wt. Fine. So I'll put wt first for some reason and I will see why. Is this fine? This is the function of these 4 variables. No problem. Now, therefore your TD0 algorithm becomes Wt plus eta t f of Wt st at st plus 1. Now, can you help me to do this? Can I make it into a martingale? Any idea? So first of all, I'll define an event collection of events ft, which is the collection. This
I
represents
just want to
collection.
ask something that
Yeah.
the reward in the previous normal equation, that's not a deterministic function. So isn't that a noise?
So we assumed it to be a deterministic function because we are considering these probabilities now. If it is not deterministic, then also it turns out to be the same equation because we have shown that the reward functions can add up.
Okay. So in this case, it is we are following a model based.
Correct.
This is
No, we are not following a model. What I'm saying is, so we have done 2 type of MTPs like S dash R S A, right? And we have done S dash S A, right?
yes.
So
Yes.
here I said that the reward function is stochastic. Even here, the reward function can be still stochastic and it could be noisy. But when I take an expectation, that term would see all that noise I will be trying to put into this single martingale. I'll show you why. It is like there will be loss terms. See errors in WT also because WT is a stochastic gradient descent. There would be error terms in phi of ST plus 1 because ST plus 1 is stochastic. Everything is stochastic right here. All of these 4 things are stochastic, right? The reward itself would be a stochastic thing, but it doesn't really matter. We'll see in the expectation.
Except ST, everything is stochastic.
Exactly. Except ST, everything is stochastic. And WT as well. These 2 are known basically because WT is what I am updating to WT plus.
No. So
but WT plus 1 will be stochastic again. That's the idea.
Yeah. So will ST plus 1.
Correct. So we will define, this is called a sigma algebra, but we're not going to know what is sigma algebra. I'll just think of it like an event, collection of events. Just basically what events? W0, S0, A0, R0. W1, S1, A1, R1, dot, 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 WT, ST. AT plus AT and ST plus 1 or RT plus 1 and so on. These I will not consider. Okay. So what are the events that I'm considering? The RT is not even there. So RT we are not going to even write. So just don't worry about R. So ST, AT, ST plus 1, WT plus 1, I'm not going to consider. So it says that at a particular time, I see all at a particular time, I see all the past WT, ST, ATs, but not particular time capital T. We see all the past ST, AT, ST comma AT for T less than equal to capital T and AT for T less than capital T. Fine. These two things I'm seeing. Basically, again, this is the events is W0, S0, A0, W1, S1, A1, and so on. Okay. W, T, ST. And I stop there and I don't put AT and ST plus 1. I don't put them in. Okay. So what I'm trying to say to you is, it's very simple. This function f, I will try to do something like this. I will try to compute the expectation of this function, f of WT, ST, AT, ST plus 1, given the collection set FT. Okay, so now here comes the martingale. That's where the martingale comes in. So all I'm trying to do is I will try to compute this.
Before you bring in the martingale, could you please explain from the like sigma algebra part, because like it was a bit too much to process, and like I was
basically it's nothing.
Yeah.
So I'll tell you. See, at a particular time, WT and ST is known, right? Correct? Just forget about the sigma algebra.
After
Sigma
that
algebra
point,
for
I didn't pay much attention.
not
because
known. This is not known. Correct? This is not known. AT and AT plus ST plus 1 not known. Do you agree?
Yeah. Yeah.
So I am saying everything that is known, I will just collect it. So I will know everything up to ST. Do you agree? Yes or no? Because I know ST, I know everything in the past as well.
Yeah. Okay.
Everything in past. That's what I wrote. I know that these two are known. Therefore, I write the expectation with whatever was known in the past. That's it. Now it is clear.
Okay.
This is everything in the past.
Yeah. Got it.
So this is basically, see, this is such a fancy way of writing what? See, everything in the past is not even required for me. What is required? WT, ST,
Only the
AT.
past last iterations.
Very good. These two are required. Bus, that's it. ST and WT is required.
Yeah, I
That's
was
all
wondering why we need so many terms. I was going to say it's a part of the MDP, right? So we don't.
Yes, exactly. Very good. We don't need it, but when we write something mathematically, we're not doing it too mathematically intensively over here. I could have very well written this. And so basically, when you define something, it's basically defined in terms of a history term. So that's why we wrote down the history, because it's a Markov chain. All those things will just go away. Absolutely right, Sean. Fine. So now what I'm trying to say is your martingale. So basically your martingale MT plus 1, WT plus 1, WT plus eta, and you have the expected value. Where is it? You have f of wt st at st plus 1. Do you agree? This is what we have now. Again, as Antariksh was telling me, see,
We
I
are gonna
can
add
write
some
this.
expectation.
Very good. Very, very good. wt st at st plus 1. This is very simple math. Once you get the hang of this thing, there's nothing in it. So this is why I'm writing the f of t. It's simple to write. Instead of writing multiple terms, it's simpler to write. And then plus f of wt st at st plus 1 minus the expected value of okay. So now we see we do get something. So let us see if this is really a martingale or not. As we can see, this term.
So the second and the third thing totally should come to 0, right?
Exactly. Given ft, that will come to 0. Exactly. Very good. So this term, people who have understood conditional expectation, can you tell me what will this be a function of? I will
WT and ST.
read that. Very good. Because these are given. These are going to be marginalized out. Marginalized out, or expectation is being computed over them. Expectation is computed over them. So as Swam, you were asking where to solve these questions. So try solving them. There are many questions I gave for conditional expectation last time as well. Please go back and try to solve them. You'll understand that whatever is not given to you, those things will marginalize out because it's an expectation. And whatever is given to you, the function, it will become a function of those parameters. Because those are the parameters that you can tweak, not the ones that are there in the expectation. So, okay. So basically, this term that I have, I replace this as mt plus 1. Can you tell me what is the expected value of mt plus 1 given ft? This is expected value of f, small f, given ft minus the expected value of small f given ft.
Yeah, exactly like the bandits one.
Exactly. So these
And
because perfect, because for the ft I know the current wt and st. That's why I'm using the ft's. This is again a constant. The inner is a constant, therefore the outer expectation can just go exactly like a bandits. So I get the martingale sequence goes to 0. Right? So my equation becomes, so wt plus 1 is wt plus eta times f of wt comma st plus 1, or at comma st plus 1, or is it no st comma wt plus the martingale. Do you agree? The martingale is f of swt st at st plus 1 minus f of st comma wt. Do you agree? Any questions? So all I wrote is I added and subtracted the expectation. I'm waiting for questions. Anything you want to ask?
like, could you just once explain the fact like this was a question in bandits as well, and I looked it up, but yeah, I get confused again and again. I mean the expectation is
What
becoming
is the
0.
question?
The expectation is becoming 0, but how does that imply that mt plus 1 also approaches 0? Just could you just explain once?
In expectation, right? So like as you go higher and higher, like that is a very good question. That does not actually mean that you're going to mt plus 1 is going to approach to 0. It is only going to mean that in expectation, this martingale will converge. That is, this martingale sequence, whatever we have over here, this martingale sequence will not contribute. Basically, so if it is a zero error, if you add infinite number of times by law of large numbers, the expectation goes to zero, right or wrong? Because you're going to add these noises at every step.
Yeah.
Add noise at every step. And if x in a on expectation,
Okay,
it
so
goes to
the
zero.
FD plus one term doesn't become zero, but on it, when we add them all by large
Yes.
numbers, when all these martingales together become zero.
Correct. These martingale terms don't contribute. So that at the end, at the asymptote, you will be in a epsilon bound. Because you have been adding martingale terms throughout by law of large numbers. This will go to zero. So that's why you have to show these terms have to go to zero. That's the idea. Okay, but what I'll do is I cannot prove this today. We'll do the entire proof, each of these things next time. But what I'll do is I'll try to compute f of st comma wt. This will take some time and we'll see how much can be go forward. We'll do as much as it possible we can do. So first tell me, this is a fun exercise to do. What is f of st comma wt? F of wt st at st plus 1. Do you agree? Given wt and st. Any questions? So we are computing the expectation. Help me out with this. So this is the practice that I was talking about. Now we'll have to practice the expectation. Anyone? Tell me, what will this be?
Okay, by lotus,
Summation.
we can get summation over AT and ST plus 1.
Okay, A and S, okay, over sum of S and A. ST plus 1 is equal to, say, S, and
Okay, we can
AT is equal
take
to.
a double summation, then we could like before the within the A's distribution we can write pi, and within the SS distribution we can write the Markov chains probability distribution, and by lotus we would
Yeah,
just
you have gone very far. We did not even write double expectation. This term is conditioned over WT and ST, right? Shubham, is this fine? This is
Yeah.
this is conditioned over f of st. So how do you remember? So expected value of x given y is what? This is x and the probability of x is equal to x given y. Yes or no?
Yeah. That's by lotus, right?
That is conditional lotus. That we have shown before. So this is exactly what I'm writing. These two are given, so I wrote them in conditioning vector and the probability, and whatever is not given, I wrote it as the probability function. Okay, fine.
Yeah.
And then lotus, as you were telling, I will just
Multiply
write
with
f
the
of
function. Yeah.
correct. STAT is t plus 1. Now, as Antariksh was telling me, what can I do now? See, I don't know this
I
function,
can
but I
bring
know
the AT
other function.
equal to A to the other to the
Very good.
condition side, and I would introduce the policy function.
Very good. That's exactly what I will do. AT equal to A, ST and WT into, as you recall, when I take, so probability of A comma B is same as probability of A given B into probability of B. Similarly, probability of A comma B given C is the same as probability of A given B comma C into probability of B given C. So given C just stays back. When you have, so given C term just stays back. Just remember it this way. We have proved this, but this is the best way to remember, as I keep telling. Next, this term becomes probability of AT, A equal to A given WT into the function f. Now tell me, What will we do? Next, what will I do? So this function, do you know this function value and do you know this function value?
Yeah, we know both.
Yes. So this is independent of WT. I don't need omega because the model parameters are known. This is what? This is the policy function. Yes or no? A given ST. Right? This is your policy function.
Yeah.
And this is
Yes.
just your P pi of S given or ST plus 1.
The transition probability.
Very good. ST comma AT. Very nice. Let us write it down in a easier, like a easy to read form. So now I will write this as A comma S. This is the transition probability of the MDP. So AT is equal to A. So I'll S prime I will write. So I think there is a lot of S's somewhere. So S is fine. S prime is okay. S prime. Yeah. S I will write as S. Okay. This is not a problem. So S prime given ST comma AT into pi of AT comma ST. Leave it. I'll just write it in this form. But this is summed. Yeah.
This looks
Tell me.
This looks eerily similar to the V pi is equal to summation of policy.
Exactly.
into
That is
action value.
exactly that's what you will get. So I will write down the F function. What is the F function? Can you tell me? Reward ST AT S dash or STS. I am summing over A. So this policy is F of WT ST A comma S dash. Fine. So what is the value of F? Can you do you have it noted down? So F is the reward function. What is it? The reward function plus gamma times the next state's value function minus state's value function, right? The reward function is a S dash plus gamma times the value function of the next state times W. Then minus pi transpose ST W into phi of S. Do you agree? This is fine. Clear? Any questions? I just replace this value of F over here. So now tell me what will be the first term as Shoham was telling me. P of S dash ST AT pi of A given ST into reward of ST AT or STA S dash. Can you tell me what is this term going to be? We have already defined this. This is the expected value of
Expected
the
reward. Yeah.
Yes. So this is expected reward at state S T. Do you agree?
Yeah.
We are summing over both action and state. So these two will just go away. This is the expected reward. Expected reward at state S as done before. Fine. This is also fine. So now the second term that I will have is what? I will have this A S dash pi of S T pi of ST P pi of S dash ST AT pi of A given ST into gamma times phi of st or s dash. Is this fine also? Second term into wt. Do you agree? Is there any calculation you want me to tell? This is the first term. This is the second term. Let us try to do the second term. Yeah, tell me. How
Yeah,
do I
got
do the
it.
second term? Second term, how do I do? So do you see this term is independent of A, right? Isn't it? It's independent of action. So this term becomes what? This is the product of S dash A given ST. Yes or no? And you're summing over
Yes,
all
yes.
actions and states and phi of S dash. So which one will marginalize out? Can you tell me? See, this term does not depend on A. Because this expectation does not depend on S. We can just sum over A and it will marginalize out by law of total probability. By law of total probability. We have, as you were telling me, we have done this for the policy pi. So this is going to be just gamma times phi of st summation over S dash p pi from S dash from state S pi of S dash into wt. Do you agree?
Yes.
So I just remove the S term by law of total probability. Now, if you have understood this, tell me what will be the third term going to be? Term 3. Term 3. That is the same expected value over all actions and states. Probability of S dash A st phi of S t phi of st dash wt. Can you tell me what will this be? This is very simple. This is term 3. See this
Could
term.
you just like in the previous term once again explain why it is not why it is independent of it?
So phi of S dash just depends on S dash, right? Just depends on st plus 1, right? So if I now wrote, so I could write this expectation like this, right? Is expectation over A, expectation over S dash pi of S dash
Okay.
and summation of A P of S dash A st. I can do that.
Yeah. So
Yes or
yeah,
no?
the A's would marginalize out.
Yes, A
Okay.
would marginalize.
Yeah.
And this
Just
equation in the third one, you understood? What will it be? Simple only. There's nothing much.
yeah. So we again marginalize the A out, and then
A
it's
and
got
S both can be marginalized out. See, this equation does
this
not
is
depend on S on A.
oh yeah right.
Yeah,
This
it's
doesn't depend
constant.
on S
Yeah.
dash.
This is a constant. So this just goes to 1. This is nothing but st phi of st dash. Okay, so we have done the major heavy lifting. So next day we'll just prove the conditions. So basically we have derived f of the famous term that we are going to use.
Yeah, the
That is
minus
R
term
of,
is actually the last projection we have.
correct. Yes. We'll be using this extensively next day for proving the theorem that I wrote down. Just go back, look at this. After this, I don't think we'll do much of proofs because this is mostly the end of it. We'll do hand waving stuff. But this is very interesting to look at. This is what practice would give you. Trying to understand expectations and things like that. This is the term that we'll be dealing with next day. This is exactly what we'll be trying to find out Lipschitz continuity on, martingale differences on, and so on. I'll just check if my terms are correct. Yeah, it looks correct. Yeah, so this is all. I think I made a small error somewhere. Can you tell me where? Yeah, I made this error here. I did not open this bracket out properly. This is fine now, no? Isn't it? This term is there in every term, correct? Phi of st. So this will also be multiplied with the reward function, correct?
Right.
Yeah. Okay.
Yeah.
There will be phi of st everywhere. Yeah, so that's the mistake I made. And I made another small mistake. I did not put a transpose over here. Sorry for that. There would be a dimensionality mismatch if I don't put the transpose. So this becomes a transpose WT because it's a scalar again. So you didn't tell me has to be a scalar, right? And this has to be phi of st. This is correct. So this can basically be written as st plus gamma times summation over s dash p pi of s dash given s pi transpose s dash WT minus pi transpose st WT whole product with phi of st. So we'll use this equation next time and we'll try to prove the Lipschitz continuity of this equation. We'll try to see a few things like Lipschitz continuity and martingale differences, and then we'll be done with TD0 algorithm. So any questions you want to ask, feel free before I stop the class today.
Yeah. So the normal gradient descent is actually can I say the normal TD0 is normal gradient descent is actually TD1 because I'm
TD1
going through all the
states.
yeah.
I have to think about it, but all the states, if you do gradient descent, it's an expectation of all the states, right? It's not TD1 takes the entire trajectory of rewards. Correct? Isn't it?
It takes the entire trajectory from S to ST plus 1 till it converts.
Correct. It takes entire trajectory and then takes the lambda to the power I into, so it's something like this, right? So lambda to the power I, and then you have the di term, the ith term of the difference. Correct?
Yes.
That's what you have in the TD learning algorithm, TD1 algorithm. So where you would have the entire di, d1, d2, TD1 means this just goes to 1, and this is d1 plus d2 and all the way to dt, correct?
Yeah, TD1 if I take all the differences.
Yes. So if you do gradient descent, it would mean that you are going to take a summation of. So in gradient descent, we have already done the gradient descent. The gradient descent update is this update, right? Is this update, correct? Right?
Yes.
So what you're trying to do is you starting from every state, you are seeing what is the value function you're going to get, right? So so this is a bit different, isn't it? So this is an expectation of all start states, expectation over all start states, right? But TD1 algorithm is like you start from a particular state and then you go on doing it, right? You don't take an expectation over the start states,
Yeah.
right?
Yeah.
So here this algorithm can be written. So this entire V pi, we can write this as the sum of the rewards, end step reward function I can write, no? So each of the states could have a TD1 algorithm, but the expectation outside is not the same. Are you getting? So where is the analogy? Where is the what is it called? Where is the confusion? Because this is a start state and not the end state, not the entire trajectory. Right?
Yeah, I get the fact that we are not considering an entire trajectory here, and we are just considering the like expectation
Start state.
when we are only at the start state, and so
Yes.
it's not a TD1. It's
Yes.
But when we are taking that function out, it becomes TD0.
That is correct, because we are taking only one step of the gradient here, one step, right? Because
Yeah,
we are
that
just taking one step. If you take multiple steps and then reweigh them, then you can make this expectation into a TD1 algorithm, right?
yeah, if we
So
had
it's
in fact calculated the expectation by a Monte Carlo type thing where we went through the entire trajectory, that would be a TD1 thing. But again, the entire point of TD0 is to not
correct.
go
The
through.
expectation would be for V pi and not over S. The S expectation is coming because we are trying to learn a value function over all states. There are two expectations over here, right? So there are three expectations. S is sampled by the Markov chains stationary distribution. Action is sampled by at every point. AT is sampled by ST, right? And ST plus 1 is sampled by ST comma AT, correct? Right? All right. So normal TD1 algorithm, we don't even consider this. Here we are trying to learn the value function for every state using this function. That's why we're considering it, no? Because in the normal state, we just keep traversing due to the Monte Carlo estimate. Here we cannot really, at starting off, the objective function is not.
It's not a traversal.
Exactly. It is like for calculating this traversal is coming here. Traversal is this. This is the traversal. Right? When we normally do the TD1 tabular case, this is the traversal, right? The traversal will be within the expectation. That is V of S, which can be represented as 1 step, 2 step, 3 step, 4 step, 5 step value loss function, correct?
Yes.
I was planning to give you a homework, which I'll give you from this TD where you will be using 2-step updates. So we are doing 1-step update right here. Correct? Yeah. What you will do in your assignment is you will do a 2-step update where you'll use a 2-step Bellman equation. Then using the 2-step Bellman equation, also you will see that the algorithm converges and all these properties you will be trying to show. That will be your homework. I'm giving you a spoiler from beforehand. That would be your exercise to understand these concepts better. Okay.
Yeah. The V pi at the end is a expected function. So when within it, it is kind of traversing, but our agent isn't traversing. That's
yes.
the
Correct.
point.
So our outer function is also a expectation. So we are basically sampling the start state based on the stationary distribution and then traversing. Outer expectation. Sample.
Yeah, so if we had gone a trajectory, we would have sampled our every first step for every iteration. We wouldn't have done.
Correct. Then you will once you sample the first state on the stationary distribution, then the inner expectation. That is sample the trajectory, isn't it? That is V pi. Now it's fine. Once you sample, yeah, there are two samplings here. That is first is the start state and then the trajectory, depending on the start state. Okay. So stop here. We'll see you next week. Stop recording. Okay.